If all diesel-electric locomotives burn fuel and move trains, why are there so many different types? Since EMD's 1500 horsepower GP7 rolled out in 1949, that single concept has splintered into yard slugs capped at 35 miles per hour, passenger units pushing 4,400 horsepower under Tier 4 emissions law, and distributed power setups that cut in train forces by 40% on mile-long consists. Every major type of modern locomotive is a precise answer to physics, economics, and regulation. The real story begins with a design decision most people have completely overlooked. In 1949, a new kind of locomotive rolled out of EMD's LaGrange plant, the GP7. At first glance, it looked plain compared to the streamlined cab units that had dominated railroads since the 1930s. But this boxy 1,500 horsepower machine quietly solved a set of problems that had frustrated railroaders for years. The post-war network was a patchwork of main lines, branch lines, and yard leads. Cab units like the F-Series were powerful, but their full-width bodies blocked rearward vision and made switching moves awkward and risky. Maintenance crews struggled with tightly integrated engine compartments, and every new model seemed to require its own set of spare parts. The GP7 turned those headaches inside out. Its narrow hood and side walkways gave crews a clear view in both directions, whether running long hood or short hood forward. This made it safer and faster to work local freights and turn trains on the fly. Under the hood, EMD's 16-cylinder 567B diesel engine delivered a reliable 1,500 horsepower, but the real innovation was modularity. The GP7's design let mechanics swap out major components, prime mover, generator, even entire truck assemblies, without special tools or lengthy shop time. For railroad accountants, the numbers made sense. The GP7 cost less to build and maintain than a cab unit, and it could be assigned to almost any job on the system, from hauling grain across the prairie to shuffling cars in a yard. Between 1949 and 1954, EMD built over 2,700 GP7s. They spread quickly across North America, replacing steam engines and setting a new standard for flexibility. One fleet engineer later recalled, "You could put a GP7 anywhere, main line, branch, yard, you name it. It just worked." The GP7's hood unit form became the template for generations of road switchers to come, anchoring the idea that a locomotive's shape, visibility, and serviceability are not just matters of style, but of safety, economics, and operational reach. Yet as trains grew longer and heavier, the limits of 4 axles and 1,500 horsepower would soon become clear, setting the stage for the next leap in locomotive evolution. Longer trains and heavier loads demanded more from North American locomotives than the 4-axle GP7 could deliver. By the early 1970s, the answer was clear: add a third axle to each truck, boost the engine, and double down on the road switcher's modular approach. The SD42 arrived in 1972, setting a new benchmark for mainline freight. Its 6 powered axles, CC configuration, spread the locomotive's weight more evenly, putting more steel on the rails and raising the available adhesion coefficient to about 0.33. That meant a single SD42 could deliver a starting tractive effort of 95,000 pounds force, nearly twice what a GP7 could muster. The horsepower jump was just as dramatic. The SD42's turbocharged 16-cylinder 645E3 engine produced 3,000 horsepower, yet the real story was how much of that power could be used without spinning the wheels. Engineers found that with more axles and better weight distribution, they could reliably pull 10,000-ton trains across the plains and up moderate grades, jobs that once required double heading or helper engines. The modular electronics, with plug-in relay racks and field replaceable cabinets, meant less downtime and easier upgrades, extending the SD42's service life across decades and thousands of units. But the quest for more did not stop there. By the 1990s, new electronics and traction motor technology pushed the limits again. Modern 6-axle road locomotives, like the SD70AC, now top 4,400 horsepower and deliver over 115,000 pounds of starting tractive effort. The key is AC traction. Advanced inverters and 3-phase motors allow real-time slip control, squeezing every ounce of grip from the rail. These machines can maintain 70 miles per hour with mile-long double-stack trains, all while meeting stricter emissions rules and burning less fuel per ton-mile than ever before. For engineers in the cab, the difference is more than numbers. One engineer recalls, "When you notch out an SD42, you feel the whole train respond. With the new AC units, it is like the power just hooks up and goes, no spin, no fuss." The evolution from 4 to 6 axles and from DC to AC is not just about brute force. It is about putting more power to work more efficiently, in service of a rail system that never stops growing. Rivalry between locomotive builders has driven every major advance in North American rail technology. After the GP7 arrived, EMD seemed untouchable, but General Electric was quietly preparing its own move. By the mid-1950s, General Electric's U25B entered service, offering a modular design that challenged EMD's grip on the market. Railroads, always seeking reliability and cost savings, began to play the two giants against each other, sparking a cycle of innovation that would shape the industry for decades. Through the 1970s and the 1980s, production soared as EMD's SD42 became a mainstay, while General Electric countered with the U30C and Dash 8. The landscape shifted again in the early 1990s when General Electric introduced the AC 4400 CEW, the first mainline freight locomotive in North America to use AC traction motors. This leap offered better adhesion and lower maintenance than the DC units that had dominated for years. BNSF's decision to adopt the AC 4400 CW in large numbers pressured EMD to accelerate its own AC traction program, resulting in the SD70MAC and later the SD70ACE. Historian Dr. Linda Porter observes, "Each time a builder gained an edge, whether modular electronics, AC, traction, or emissions controls, the other would respond within a year or two, and the whole industry would shift." The rivalry became an arms race. 6-axle frames became standard, modular electronics the norm, and every procurement decision a battleground. Corporate transitions added complexity. In 2019, General Electric's locomotive division merged with Wabtec, consolidating control over critical components. EMD, after passing through Caterpillar, became part of Progress Rail in 2022. These shifts influenced major purchases, like Amtrak's choice between the Genesis and Siemens Charger. Amtrak's selection of the Charger, driven by Tier 4 emissions standards and lower fuel costs, signaled a new phase, one where environmental regulation and total ownership now shape the contest as much as horsepower or speed. Each locomotive today bears the imprint of this ongoing rivalry, from cab design to the code running its systems. Inside a modern classification yard, the locomotive's job is a relentless cycle of starting, stopping, and dragging heavy cuts of cars at walking speed. Unlike their mainline counterparts, yard switchers are built for torque, not speed. Their gear ratios, often around 60 to 17, about 3.5 to 1, convert the engine's output into raw pulling power. The result is a machine that tops out at 25 to 35 miles per hour, but delivers steady force where it matters most. In the yard, this is not a drawback, it is essential. The EMD SW9 and SW1000 families, each producing 1,200 horsepower and riding on BB wheel arrangements, embody this approach. Their compact frames and central cabs offer clear sight lines, a necessity when threading cars through crowded tracks. Smaller fuel tanks, roughly 2,500 gallons, keep them nimble, while oversized radiators and robust cooling fans allow for continuous tractive effort. At just 3 to 5 miles per hour, a switcher can pull up to 80,000 pounds, hour after hour, without overheating. Here, the true measure of performance is not peak horsepower, but the ability to apply force steadily, shift after shift. When the work gets tougher, with longer cuts and steeper grades, the solution is the Slug. Unique to North America, a Slug is a locomotive stripped of its engine, loaded with concrete ballast, and equipped only with traction motors. Paired with a powered mother unit, the Slug draws electricity through heavy jumper cables, turning its axles into extra sources of tractive effort. There is no extra diesel to fuel, just more wheels gripping the rail. A typical setup, a 2,000 horsepower mother and a 4-axle Slug, acts as a 6-axle unit, pushing starting tractive effort to 75,000 pounds or more. The added weight and traction motors help prevent wheel slip, especially when dragging long strings of cars up a hump or out of a deep bowl. Railroads like Union Pacific and BNSF still use mother Slug pairs for the toughest yard jobs. The economics are clear. Slugs cost less to maintain than full locomotives and can save up to 18% in fuel per shift. Maintenance is simpler, with no prime mover to service. For yardmasters, the ability to add or drop a Slug offers flexibility as traffic ebbs and flows. Every detail, from gear reduction to ballast, is a direct response to the demands of slow, heavy work. Locomotive design splits here, with yard switchers and Slugs forming a branch built for controlled force and adaptability. In the late 1970s, passenger trains demand a kind of performance freight locomotives rarely face. Amtrak's F40PH answered a clear call: get up to speed quickly, stop reliably, and keep a dozen coaches powered with lights, heat, and air conditioning. Its 3,000 horsepower, 12-cylinder engine paired with a head-end power generator, delivering up to 750 kilowatts of electricity for passenger comfort. Unlike freight units, the F40PH was geared for acceleration and could reach 90 miles per hour in under 12 minutes with a standard consist. The real innovation was integrating HEP, head-end power, directly into the design. Early F40PHs ran the HEP alternator off the main engine, forcing it to run at a constant high RPM whenever coaches needed power. This kept amenities running but wore out engines faster and burned more fuel, a compromise railroads accepted for reliability and simplicity. By the 1990s, Amtrak needed more speed and efficiency. Enter the Genesis series from GE. These units delivered 4,200 horsepower from a 16-cylinder engine, with a streamlined, shark-like nose that cut drag at high speeds. At 125 miles per hour, even small aerodynamic gains saved thousands of gallons of fuel each month. The Genesis used an integrated generator, drawing HEP directly from the prime mover. This improved fuel economy and simplified maintenance, but required the engine to balance traction and electrical loads in real time. On long-distance runs like the Lakeshore Limited, Genesis locomotives could maintain higher speeds and use less fuel per mile than the F40PH while meeting early EPA emissions standards. The Siemens Charger, introduced in 2017, set a new bar. Its 4,400 horsepower Cummins QSK 95 engine meets strict Tier 4 emissions standards, using selective catalytic reduction and diesel particulate filters to slash nitrogen oxides and soot. The Charger supplies 1,000 kilowatts of HEP, enough for bi-level trains with full climate control and Wi-Fi, and accelerates a 10-car consist to 125 miles per hour. Its streamlined shell and roof fairings further reduce drag, while advanced computer controls optimize both traction and HEP output. Procurement records show Amtrak and several states chose the Charger for its projected 30% lower lifecycle fuel costs and Tier 4 compliance, now mandatory for new passenger power. Each generation of passenger locomotive reflects changing priorities, speed, efficiency, and emissions, driven by technology, economics, and law. Unlike freight engines, passenger units are built for acceleration, a constant electrical supply, and ever stricter environmental rules. On mountain grades and endless plains, the length of freight trains has crept ever higher, pushing the limits of what a single locomotive at the front can control. As trains stretched past 2 miles, a hidden problem grew: the force at each coupler. Railroads call it drawbar force, the tension that tugs every car forward. When all the power comes from the head end, the first few cars bear the brunt, sometimes enough to snap a coupler or trigger a derailment. Physics sets a hard ceiling. Too much force at one point, and the train risks tearing itself apart. The solution arrived not with stronger locomotives, but with a new way to spread the work. Distributed power units. Place remote-controlled locomotives deep in the train or at the rear. Instead of one giant pull, power is applied at several points along the consist. Modern radio control systems synchronize throttle and brakes between lead and remote units, reacting in milliseconds. The effect is dramatic. By sharing the load, distributed power units cut peak drawbar forces by up to 40%. This single change lets railroads safely run longer, heavier trains, sometimes over 15,000 feet, without overstressing the couplers or rails. A turning point came in 2004 when a Union Pacific coal train derailed on the Feather River route. Investigators found that excessive entrain forces, concentrated at the front, had caused a catastrophic run-in of slack. Within months, Union Pacific began equipping trains with mid-train distributed power units, and the results spoke for themselves. Not only were forces tamed, but train length limits grew by 15% with no extra locomotives needed. Other railroads quickly followed. Today, distributed power units are standard on long-haul routes, their presence a direct answer to the mechanical realities of force management in modern railroading. The real strength of a modern locomotive lies in its traction system, the sequence of machines that turns diesel fuel into forward motion. For years, North American freight trains depended on DC traction motors, rugged, straightforward, but limited. DC motors struggled with wheel slip at low speeds and required frequent maintenance for brushes and commutators. As trains became heavier in the 1990s, these limits became costly. Railroads needed more pulling power and less time in the shop. A C traction driven by new power electronics offered a solution. In AC locomotives, the diesel engine spins an alternator, generating alternating current. This alternating current is converted to direct current by a rectifier, then sent through an IGBT inverter, a bank of fast-switching semiconductors that reshapes the current into variable frequency, 3-phase AC for each traction motor. This chain allows precise slip control and torque adjustment, extracting more usable force from the same weight. The payoff: up to 13% more tractive effort and a 1.8% drop in fuel use per mile compared to top DC units. Norfolk Southern's Juniata shops put this technology to work, converting Dash 9 DC locomotives into AC44C6M models. Each rebuild replaces DC motors and controls with AC induction motors and modern inverters, extending service life by a decade. The economics are clear. Rebuilds cost less than half a new AC locomotive and pay off in 5 years through fuel savings, lower maintenance, and better reliability. For railroads, switching from DC to AC is not just about power, it is about staying efficient and competitive. Federal rules have quietly redrawn the map of North American locomotives. In 1997, the Federal Railroad Administration ordered 4 ditch lights. 2 at each end, and impact-resistant glazing for cab windows. These requirements, adding 150 pounds per cab, nudged even established models toward new priorities in safety and design. A 5,000-gallon fuel tank soon became the norm for road units, offering roughly 1,800 miles between stops, while yard switchers settled for half that, reflecting their short-haul routines. Regulation also sparks invention. Genset locomotives arriving in the 2000s split power among 3 or more small diesel engines, switching them on or off to match demand. This modular setup trims fuel use by up to 30% and helps meet Tier 4 emissions standards, but higher maintenance and reliability issues have kept them from widespread adoption. Railroads tested gensets in air quality hotspots, only to revert to proven AC units with after-treatment systems when problems surfaced. Passenger lines found their own solution in non-powered control units, cab cars with no engine that let one locomotive push or pull without turning at terminals. Research and training units, meanwhile, serve as rolling labs for hybrid drives and alternative fuels, logging limited miles but shaping future fleets. As historian Dr. Linda Porter notes, regulations and experiments quietly steer the industry, their impact surfacing years later in unexpected forms. Every locomotive type, from the 1,500 horsepower GP7 to 4,400 horsepower AC road units, yard slugs, and Siemens Charger passenger engines, answers a real-world constraint: gradients, labor rules, emissions law, or a 5,000-gallon fuel run. These aren't cosmetic variations. As freight demands shift, emission standards tighten, and new hybrids emerge. Each design reflects a negotiation between physics, economics, and law. The locomotive's future will be engineered, one problem, one solution at a time.